Good morning, everyone. First of all, thank you so much for joining us today here at AI House in Davos 2025. And I'm Teruo Fujii, President of the University of Tokyo, and I'm the moderator here for the session titled AI and Physics. I'm very much excited about listen to all these physicists and about how they are looking at this AI technology in their daily research work, and also so of course AI could be a very good tool, as I have already told here on the first day about, for example, we could use it for example, simulating the development of the universe itself. But at the same time, we can do many things from a physics viewpoint and how AI is behaving. And this is really a kind of huge number of parameters, a system out of a huge number of parameters. And then it will be very interesting to have a look at this AI itself from the physics viewpoint. So that, let me start with, let them introduce themselves briefly and how they are involving this AI technology into their research work. So that, okay, so first of all, Professor Max Tegmark from MIT. So please, yeah, go ahead.
Thank you. So I'm Max Tegmark. I've been doing AI research at MIT for many years, but I'm in the physics department, so always a physicist in my heart. Super excited about both what AI can do for physics and also what physics can do for AI.
Then you can also.
Oh, I want to give everybody else a chance.
Okay.
I'll talk more later.
Oh, okay. So then Professor Lenka Zdeborová from EPFL, please.
Yes.
Yeah, so you can also talk a little bit about what you are doing.
Yes. So my name is Lenka Zdeborová, and I'm a professor at EPFL, not far away from here in Lausanne. And I'm also in the physics department, but also jointly in the computer science department. My background comes from statistical physics, that's a part of physics, and theoretical physics. The way I'm looking at AI in my work, in my research, is the following. Nobody in this panel will be surprised that physics is trying to understand the universe. That's kind of the origin of why physics is there, or one of them. But AI and the way neural networks work today is also a system that appeared in the nature, maybe on a computer, but computers for me are still part of nature. So I'm looking at it at AI as an object of study, and with the tools of theoretical physics, try to understand how actually it works, what are its limitations, what's the best possible performance we can get, what would be potentially the dangers. So in the same sense as what statistical physics does, it takes the molecules in this room and looks how they actually interact together, and how from that it appears that the temperature is 21 degrees. And in the neural networks, when we actually train them, what's happening in the computer, we take the weights that we adjust, and they interact with each other through the data. So conceptually, it's really the same thing happening there. And when we want to understand where it goes, it really is the same mathematical tools that are used to understand the air in this room or the behavior of the neural network as it is trained. So that's my main interaction.
Okay, thank you. Okay, so then let's move on to Professor Koji Hashimoto from Kyoto University.
Thank you. I'm a particle theorist working in quantum gravity and also particle theory in Kyoto University. My group was founded by Professor Yukawa. He was the first Nobel Prize laureate in Japan. And his work actually opened up the microscopic space and physics notion. And we are following his legend. And I'm also a director of a machine learning physics initiative in Japan on my T-shirt. And this is like 60 professors in Japan, and also a community of 1,000 researchers all over from Japan, from companies and universities and such. And we are enjoying AI physics unification together. And the reason why, in particular, young people are gathering this community in Japan is that, in fact, as Lenka said, our way of seeing the universe or the reality in physics is just discovering some laws on physics and fine-tuning what is happening in this world. And on the other hand, AI is doing actually the same. AI is perceiving the reality and the world by computation. So the target is the same, and what we do is just a difference of the technologies. And in fact, those technologies are both in mathematics. So which means that, in fact, they are almost the same. So it's very similar to each other. So we find the possibility of unifying those two, and that's what I'm going to do.
I see. So it's a sort of, I mean, you could see the parallelism in between physics itself and the machine learning itself.
Yeah, as for the strategy and also the method and also the targets.
I see. So, okay, so maybe we will discuss about it later. But okay, so then we move on to Professor Junichi Tanaka, who's from the University of Tokyo.
Hi, so thank you for having me. So actually, I'm an experimental particle physicist. Maybe other person is a kind of the, I think the theorist, but I'm an experimentalist. So actually, I'm mainly work on the data analysis at the LHC. You know the LHC, Large Hadron Collider, Atlas experiment at Geneva in Switzerland. So actually, yes. Concerning the AI, the use of the AI, of course, in the data analysis, we are using the AI in the many parts. So actually, maybe the most famous result from our experiment is the discovery of the Higgs boson in 2012. And I made a significant contribution to this discovery. So actually, I think most of you may be not familiar with the kind of the collider. So that's why I'm briefly explain. So actually, in our experiment, we use a accelerator, which is not a GPU, okay? A particle accelerator, okay? Particle accelerator to collide the protons. And each one collision is called the event. So that's why our task is, for example, we want to separate a signal event from the background. This is our task. So that's why we apply the AI to kind of the classification task. Okay. So that's why in practically we are using the AI for many parts. For example, also we are using the for example, a transformer for the several different particle identification. Also, we are using the anomaly detection technique for the new particle search. And also, we are developing the detector simulator using the generative AI. So that is our current status.
I see. Yeah. I see. Thank you. I'm just curious. I mean, with this Atlas or LHC experiment, how big is the size of the data that you're dealing with?
Actually, I think so far maybe we have a 10 to 10 or 10 to 11 events.
Right. So that's exactly, I mean, comparable to the kind of, I mean, cutting edge Gen AI parameter scale.
And just so you appreciate what a big number 10 to the 11 is, that's how many stars there are in the Milky Way galaxies. And that's how many galaxies there are in our known universe. So it's incredibly large.
So that's why we need AI. If not, of course,
exactly. Okay. So let's move on to the first question that I want to ask all of you. So that we are, I mean, with this, I mean, hype, and so we are looking at so-called artificial general intelligence or super intelligence type of discussion. And then, so if you look at this physics methodology in physics, and then we would like to see what would be this, I mean, general intelligence or super intelligence looks like. and what would be the characteristics that we can, extract from those, really much, generalized intelligence. And in that context, I would like to listen to your opinion from the physics viewpoint.
Thank you.
Yeah.
I think it's very appropriate to talk about that here because I'm going to argue that physics has played a key role both in creating the AI revolution and also in finding the solution that I think we need to have a good future with very powerful AI. For the first part, we physicists tend to have a much higher standard for what we mean by understanding something than most other people. So many people throughout the ages looked at the sky and they saw these planets moving around and the sun shining, and they're like, yeah, there are these constellations and the sun, maybe it's some giant fireball or something, whatever, and then they go back to thinking about other things. But physicists said, we don't really understand this. And then they studied it hard and realized actually the planets are going in ellipses, and that can be explained by a universal gravity law that falls like the square of the distance in the sun, fusion reactor, et cetera, et cetera. And the same thing has happened when physicists started to look at the mind and had this idea that actually the brain is a bunch of quarks and electrons moving around, and so is everything else. So this must be a physical process, intelligence. It must be a process where these particles move around to process information. And it doesn't matter whether the information is processed by carbon atoms in neurons and brains or by silicon atoms in our technology. This is the fundamental insight, I think, which has enabled us to go from cogs and wheels to punch cards to all sorts of different things. And now we have GPUs. Keep swapping out the type of atoms we use, et cetera. But the information processing races ahead. I think the exciting thing and the scary thing about this is it's also obvious if you're a physicist that even though you are all very intelligent, there's no law of physics that says that this is the most powerful information processing you can make. Your brain is limited in size by your mother's birth canal. Go tell that to Demis Hassabis or Sam Altman, and they're not, or DeepSeek, they're going to laugh.
It co-evolves. It co-evolves the two together.
Yeah.
Right?
But we're never going to be able to have 1 million times bigger heads. So whereas we hear Sam Altman saying we're going to get AGI this year, even Jan LeCun is talking maybe 5 years from now. So we have to think hard about how we're going to deal with things, machines that are much smarter than us. So physics, I think, has a good lesson here also. If you compare this with nuclear physics, we want to be able to produce large amounts of nuclear energy, but we want it to be controlled energy. In a well-built nuclear reactor, and we would like to avoid things like what happened in Fukushima, and we certainly don't want like a global thermonuclear war. So the control is the key here that we physicists can all agree we want. So if we make super powerful intelligence, it's equally important that it's controlled intelligence. Alan Turing said already in 1951 that if we just go ahead and make machines that are smarter than us in all ways, we're not just making another technology like steam engines or the internet. We're making a new species, of course. You can have robots much smarter than us that build new robot factories, make more robots. And he said, then the robots will just take control. It's pretty natural that the smarter species controls. If you go to the zoo here somewhere in Switzerland, it's the tigers are in the cages, not the people. And it's not because we're stronger, it's because we're smarter, right? So that would be an incredibly dumb thing for us to do if all we do is build something much smarter than us and we can't control it. It would be equally dumb to building nuclear reactors that just explode. So physics can solve this too, though, because there is actually, and it's been a huge amount of progress by physicists, for example, in the field called mechanistic interpretability in AI. Basically, you just look at a black box AI system like ChatGPT 4 or whatever, and you try to figure out what it's actually doing. And in the last 2 years, there's been a revolution. We can now map out and see that, for example, the millions of concepts in there correspond to geometric shapes that look like crystals and circles and all sorts of things. We can figure out a lot about the algorithms that are being discovered in there and start figuring out to what extent we can trust things. There's also enormous progress in making AI not just produce text and images and videos and code, but also producing proofs. AI is beginning to revolutionize proving in mathematics. And we work in my group a lot on using AI to prove things instead about computer programs. Amazon Web Services just completed a massive project where they proved that the whole AWS login system can never be hacked. There's no more bugs left. They found all the bugs and have a rigorous math proof that they have the safest cloud out there, which is a great sales pitch for their customers, right? But it costs a ton of money because they have to pay humans to do the proofs. That's all going to change. I am confident that very soon we can actually have AIs write the proofs. And you might wonder, how can I possibly trust this if I don't understand the AI, the proof is too long to read? But I just want to leave you with a piece of optimism here. We actually, just like it's much harder to find a needle in a haystack than to verify that it's a needle after you found it, it's much harder to program up some AI tool and find the proof that it meets your specifications than it is to check the proof once you have it. You don't have to trust the mathematician who says they proved the Riemann hypothesis. You give it to your math friends and they check it quickly. So, and you can do it with a very short computer program that you can. So the long story short is, it is going to be possible to build very smart AI that we can control. Unfortunately, that's not the direction we're going now. And so many, when a bunch of people are saying, oh, we should just build superintelligence as fast as possible. But we can do it. And if we just agree as a society that people shouldn't be allowed to sell AI that they can't control, then we will have a wonderful future where the AI empowers us rather than overpowers us.
Okay, thank you so much. So that I would like to know how far we have come already, and then for the to be able to establish this controllable AI. So that Lenka, if you have some inputs to that?
Controllable. I wanted to go back to the original question about what it actually is general artificial intelligence, because when we ask such a question, the first way of thinking is that we somehow want to compare to humans, because there's the other intelligence that we kind of see around. And there I would like to kind of stress and reflect on the understanding, because in order to define something by comparing to something else, well, we first need to understand this something else. That means understand how intelligent we are and what it actually means for a human to be intelligent. But then of course in neuroscience, in medicine, in psychology, this is all studied. But fundamentally, it's not clear to me, or mathematically, why understanding what does it mean for a human to be intelligent would be simpler than to actually understand what are fundamental limits of what it means to be intelligent. Because human is just one realization of this intelligence that was kind of constrained by the evolution and how Earth evolved and the universe and the physics. But when we put these things aside, and the fact that at some point we had to compete with the dinosaurs and things like that, when we put this aside, what is actually the extent of intelligence to which we can go? So I don't know whether one would call this general or something else, or maximal, but what this actually means. And we have very little understanding, reflecting, we understand so very little about how artificial intelligence actually works. In the following sense, you would say, what do you mean we don't understand? It really goes to what we mean by understanding. One way you can say, okay, if we know how to program it, we know how to write a code that actually runs it, then we understand it because we created it. Okay, but that's one way. So in this sense, we understand what we have there. But in the kind of more involved sense in which physics would want to understand things, is that we programmed it, but do we actually still understand? Can we predict how it will behave? And this we absolutely don't understand. Ask any engineer when they will change this parameter, do they have a notion how that will actually influence their system? They don't. It's essentially trial and error. So coming with the fundamental laws that actually constrain how complex and intelligent this thing can be, that's where, going back to what we said originally, I see the role of physics in the future being very prominent.
Okay, thank you so much. So then, if that is, if you program it and then with this parameter, then if you could, for example, predict how it will be behaving, and then that is more like a kind of intelligent entity. That is what you said. So it's more like a kind of predictable. What you did was so it's more like a trial and error process for now. But
I guess what I'm saying, to even properly define the general
problem,
artificial intelligence, we really kind of need to go after what is possible, and we are so far away from this. So we should start with the understanding. We can, of course, always put some definition, but to have a definition on which we will all agree and that will become the definition, the understanding has to precede to even come up with the definition that will stay.
Afterwards, yes.
Can I add a comment briefly on that? Because I agree exactly with what you're saying. We really don't understand how today's powerful AI systems work. But I just want to add some optimism here. 150 years ago, nobody had a clue how birds could fly, how they worked. So people, for that reason, thought it was going to take very long to figure out how to build flying machines. And then physicists came along, and the Wright brothers, and maybe we don't need to understand how birds fly. Maybe there's a simpler way. And that's how we got airplanes. And if the same thing happened again, most of my colleagues thought even 6 years ago that we had to wait until 1950 or 1945 to have machines that could master language and knowledge at the level of ChatGPT-4. But they were all wrong, because we have it now, because there was a simpler way to do it. We still don't understand how the brain works. And what we physicists do, if Lenka figures out, if you figure out a new algorithm for flying a rocket ship or something like that, right? We're not going to put your brain, you, to fly the rocket. You will write a computer program that implements the awesome discovery you've made in a form that's easier to understand. And then we deploy that. And this is exactly my vision for tool AI that's very smart and trustworthy too. We ask the AI to learn the stuff and then program it up in a different, simpler way that we can understand, and then prove that we can trust it. So I think it can be done if we have the right incentives. The only problem is we're closer to building super smarter than human machines that we don't understand than we are to figuring out how to control them. That's why we need some governance. No physicist in the right mind would suggest having no safety standards for nuclear reactors, right? So it's equally crazy that right now in San Francisco, there are more regulations on sandwich shops than on AI companies.
So the thing is, for now, it's not simpler, representation than even more complex. But by the way, so, okay, please, Professor Hashimoto, so if you
yes.
make some input.
So I think we need a theory to actually control AIs. And if we look back the history of physics, for example, in my field, there's nuclear physics and particle physics. Like in 1960s, we find many hadron particles in experiments. And nobody actually can explain them by theory. And now, after that, there are many theories which try to actually formulate all of those experimental results. And finally, several theories were selected, which actually minutely and precisely describe those hadron particles. And that becomes a part of this standard model of particle physics. So it took more than, I think, 20, 30 years to establish this theory. And now we have this great theory which can describe all of those hadrons, and that can be simulated on supercomputers. And now we see this phenomenon of AI. AI is producing many phenomena in front of us. We don't know how to interpret it. We don't know a concrete, great theory to describe all of those behavior. So we need to develop many theories. So physicists are looking at those phenomena quite nicely with the help of mathematics. So we develop many theories, and among them, maybe, as history tells, some unified theory of AI emerges with the help of AI, I don't know. But that is actually the way we can actually find our future bright. I think that's the point. And now, if you ask me what's the definition of singularity, in my point of view, singularity is just find a collaborator which is computer. Okay. So far, my collaborators are human, but maybe from this year, next year, my collaborator will be AI. Since there is, for example, a Sakana AI company in Japan, which actually automate all the scientific process of writing a paper from the scratch. So if I ask...
it already is. AI just wrote half of my exam for the EPFL physics students for next year.
But it's not the level of collaborator, right? So I'm saying that it's a level of collaborator.
It felt like a collaborator.
Oh, great.
Oh, yeah,
Yes.
already.
It's gradually but rapidly changing. And my worry is that it will demolish our community of physicists to invent more theories, to understand the natural and human behaviors. And since this rapidness of the development of AI is quite great, so I'm worried about that, yes.
So that many of those theories will be generated by the AI itself.
Yeah, of course.
That would be a kind of...
Yeah, so we are
we
collaborating.
are coming very close to such kind of situation. Okay. Thank you. So then what would be the inputs from Professor Tanaka?
Yeah, actually, so I can say about AGI. I mean so in my field, so I think sometimes I'm asked about AI can find new physics. Maybe at the moment, probably no, because what we are doing is just we are using the AI as a tools. I mean, I think the AI can accelerate our research, but I think this is a kind of the AI help us to improve our data analysis. So this is not the discovery of the new physics. If you want to say the AI can find discover the new physics, in this case, maybe AI need to propose a new model, new physics models. So, for example, in case of the Higgs discovery, so as you know, so the Nobel Prize is received by theorists, not the experimentalists. So, I mean, they propose a new theory which can describe the how to obtain the massive particle, but keeping the local gauge symmetry. So such a proposal, if AI can propose such a idea, in this case, maybe we can say that probably we have a kind of the AGI. So these are my idea,
I see.
opinion.
Thank you. So, but it's what you said is a kind of contrary to what Professor Hashimoto says. And so may I ask, for example, what would be the problem that AI would solve, and then what kind of problem that you can have a look at to see or to discuss about these new theories on AI?
Yeah.
What would be the problem?
Yes. So apparent distinction between what AI can solve and what AI cannot solve is that in physics, of course, there is experiments, and experimental people actually implement all the machineries and focus on some very important but difficult quantities and measure it, and there is a feedback to theories, right? So if this experimental part is missing, then I think AI can actually help us a lot. So, for example, in the case of a simulation, if the simulation cost is not so high, then AI can propose the code and idea, and also they deploy it, and then they measure the results of the simulation, and they interpret it. So this kind of closer to maybe mathematical physics rather than experimental physics. In those kind of fields, of course, it depends on what kinds of fields I'm talking about, but there are several fields which can actually be improved by a very small cost of numerical simulation, which can be deployed only by AI, and that kind of field may be actually developed so rapidly compared to the others.
Yes. But I mean, if you're looking at this theory for AI or theory of understanding AI, so then we will also need to have a look at what a certain problems that you are dealing with by AI, right? So that what would be a kind of, for example, so if you think about this, I mean, general intelligence type of thing, and then what would be the kind of problems that we need to deal with, or we need to looking at? I mean, like a kind of standard, I mean, problems or standard, I mean, yeah, Max?
Yeah, I think it's really fun to look at applications from physics there, because we just had the Nobel Prize in chemistry go to work done by AI, and it wasn't just interesting theoretically, but it actually shows how you can fold proteins and speed up drug discovery and produce new medicines much faster. I think it was a wonderful Nobel Prize. The Nobel Prize in physics, of course, also went for AI, but that was more physics for AI. If you look at AI for physics, I would love to hear actually what wish list you have. Which of the physics problems would you like AI to help us solve quickly for just impacting society? I'll throw out some examples first. I would love if we can use AI for material science and discover a room temperature superconductor that's also really cheap to mass produce. It would do wonders for our energy distribution and climate. If we then had, you could generate amazing solar power in the Sahara and send it through a superconducting cable up to Switzerland, and you know, I would love if we can use AI for physics to figure out ways of making much higher energy density batteries that are incredibly quick to charge and discharge. I'm curious what other wishes you have.
I mean, along these lines, we could learn to control the plasma in the tokamak so that the fusion energy is finally working, and hopefully safely, so that we don't need to we can stop thinking about our energy sources. And at the same time, the materials, if we had, we could capture the carbon back from the atmosphere and do, in a sense, what we want with it. So essentially, all the challenges that physics poses itself, all those, I would kind of reflect what it can do and what it cannot do. Like, so far, it can do many things, but there needs to be data there on which it is based. And also some of the, I could imagine AI solving some of the famous conjectures in mathematics because they are well posed. Everything is defined and it is clear what needs to be done. It's just that the proof needs to be constructed and the construction is complicated, and if it exists. And we didn't come up with that. So that's something that I would imagine it possibly can do in near future. But as you were saying, kind of coming up with the questions, posing the questions on a high-level question, how to improve the society, what is the solution? It's not a well-posed question, it's an ill-posed question. So really posing it well, what does it really mean to improve society? On these kind of things, it's not really useful yet, at least from where I see it.
And then what about kind of theoretical viewpoint? So if you like to understand what would be the kind of principle behind this large-scale AI or large-scale, for example, language models, and then what would be the kind of question that we need to pose, and then so if AI can do something, and then out of this result you could, for example, find out some of the theories that you will need to understand AI, or so how would be the kind of this understanding process of AI? So that is my.
So from my point of view, like if I may.
Please.
Go on.
Yeah, please.
So from my point of view, there's like no fundamental reason why AI could not do anything that we can do. Simply because, I mean, sorry to break it to you, but we are also just a result of an algorithm that ran for millions of years and that made our brain what it is. And there is no fundamental, I mean, okay, unless you believe in God and you believe there is something else, which of course you can, but that's not in a sense how science progresses. So if you go in the scientific way, we don't have any scientific reason to believe that there is any fundamental limitation not to be able to do something that our brain does. So what is missing currently, we live in society, we interact with the world. So the AI as it is today, it has a fixed task on which it is trained. Sometimes some large language model is trained to interact or play against another one, so they somehow interact. But they are not released to the world and they don't interact with the world. So this is so far limiting it from also acting on the world. But so this is missing, but obviously, and reflecting to what you said, we don't want to release it to the world because we have no control of what it could do. So we first need to think really hard to actually understand what is safe and what is not safe, and then put that element in if we kind of want to make it as useful as it can possibly be.
I see. Thank you. So yeah, that is a very important point that I could see. I mean, like interaction with the real world or physical world by AI. I mean, controlled by AI, for example, would be a kind of very important, but somehow scary. So there's some scary part.
You can have tools that are very controllable also, like when you do physics experiments or chemistry experiments or biological experiments, there are a lot of boring lab steps where the grad student would love if they can have a robot that does it for you. And I think Japan has been a real leader in robotics ever since the beginning, and that's a great example again of tool AI. I never lost 1 minute of sleep worrying about Japan losing control of the Asimo robot or something like that. So obviously you can have a lot of wonderful experimental physics assistants that are where you can guarantee that you can control it.
I see. Thank you so much. Yeah, that's a good point. So yeah. So is any comment from Professor Hashimoto?
So if I can add one in the wish list, then I want to do a computation of quantum systems. So every system in this universe is based on this microscopic quantum world. This year is the Quantum International Year. And but if you want to actually compute things based on this quantum mechanical Schrödinger equation, it costs a lot of computations. And in fact, AI can help us to compute those things quite much. And in those cases, in fact, we don't need data. We just have the equation, and we just want to solve it. And the neural network actually can help also in this way. So there is no need of interaction with the real world. We have the fundamental equation which needs to solve. So this is another way. So in addition to this robotics, another way of using AI.
I see. Well, that's a very interesting. Scope. Yeah, this computation quantum system.
Yes.
Yeah.
Can I add some comment on data real quick also? Because I don't think we should be so worried in physics about not having enough training data. We can often make our own. Just like AlphaGo made its own training data. We have if you want to figure out why is the proton 1836 times heavier than the electron, we know how to calculate it in a way, but some of these calculations are incredibly expensive. Enormous compute resources go into it. Or if you want to know if you collide two black holes like this, what percentage of the energy comes out as gravitational ripples in space-time. We know how to compute it, but it's just so expensive. So we can use these expensive methods we have to generate data, and then use AI to find methods of computing the same thing much more cleverly and efficiently.
But the examples that are kind of the prominent examples, like the reasons for which something like AlphaFold was developed, it really was the data. It's really the protein community over the past 20 years and the developers of the experimental techniques over the past half century that made the data set on which it was trained, right? So I agree, but that's in a sense for the future still a bit.
That's why we still need you and other experimental physicists.
But I think I don't actually. You said you don't need a kind of the data, no?
Well, yes. So if I have actual equation which need to be solved, if I know this equation, then the goal is to find the solution of this equation.
So it means
then I don't need data.
By solving the solution, getting a solution, it means we can have a kind of the how to say the ultimate network. You mean?
Yes.
To describe our universe.
Yes. But of course, to find this equation itself as a physical law, I need the data. The experimental data. And from experimental data, maybe AI can help us to find the physical law or assist us to find the physical law. That is another use of. There we need data, yes.
I don't know how do we identify it. I mean,
Well, so unfortunately, there is no good examples of how AI can. So in the case of particle experiment,
Yes.
the good physical observables quantity, can AI find it? We don't have a good example yet. But in the future, I'm sure that yes.
But it's also maybe important to know that for some equations, solving them actually is not possible computationally efficiently, right? So there would be actually fundamental constraints why it is actually not possible. And those may come from physical laws, like you cannot fly faster than light, or from computation laws. If something is fundamentally computationally hard and needs exponential time, then it will not happen.
No.
And that's where kind of not understanding the boundary of what actually is doable also prevents us from, actually being sure that we can do something like what you're saying, because this equation might just fundamentally not be solvable efficiently.
Yeah.
And we don't know, right? Whereas when I was saying we are sure that it can do everything that we can do, because within the computational constraints that are mathematical and within the physical constraint that hold on the Earth, our brain was created. So at least what our brain can do is truly possible. Maybe not next year, maybe in 1,000 years, somewhere in between, who knows? But questions like that may not even have a positive answer, right? So we don't know where the boundary is.
But then so what I understood is, so if I'm correct, so it's somehow the problem itself or question itself should be, grounded somehow at a certain point, grounded to the actual or real world.
Sure, I
Like
agree with
at the level
Lenka's
of,
opinion, yes.
choosing this equation, for example.
Yes. So, so it's a kind of a philosophical question. So, what kind of equations we need to use, and it's according to Tegmark's mathematical universe hypothesis. That, for example, so some of us actually believe that the equations which govern the universe needs to be solvable,
Right.
and computational.
Yeah.
And so, if you believe in this kind of thought, then so physical law should be computable, and AI can handle it.
So that should be, realizable. So it could be realized, right? Yeah. Okay. So we have so there's a little bit time left, so that I want to take some of the couple of questions from the floor. So if you can you just raise your hand? Okay. And then you can identify yourself first.
Hi, I'm Elvis. I'm a co-founder of a humanoid robotics startup, but I'm not actually going to ask about that. You already mentioned robots for automating labs. I have a question specifically about interpretability and understanding intelligence. So it's kind of become apparent that all these techniques like mechanistic interpretability, or even like techniques based on like statistical physics and so on to understand intelligence, could work and could be applied because the object of study, that is like the current level of models, are already there. How do you think it's possible to kind of have this leapfrog the state of the art of actual models out there? How can you make something safe before it actually exists?
Now you're sounding like John LeCun. We figured out how to make nuclear reactors not explode before we built the first nuclear reactor. And if we figure out how to make drugs safe before we start selling them to the general population, right? If you go into the FDA and say, I have my new super drug, I'm going to start selling it tomorrow. I hope you guys can make it safe first. They'll just laugh you out of the office. Say, hey, where's your clinical trial? So if you treat the AI industry at least as strictly as sandwich shops, you have to have some safety standards you meet before you release the product, then companies will innovate enormously to figure out that how they can meet them. If you tell companies that they have to figure out how they can keep their things under control, then by definition, there's a race to the top. They'll put the top people on it, and the only things that come out are safe. So I'm very optimistic that we can fix this. We just need the politicians to wake up and treat the AI industry like everybody else. And mechanistic interpretability, you don't have to understand exactly everything to know that it's safe.
Did the last few days made you confident in terms of the politicians waking up?
Well, the last few, you mentioned my book. It's very kind. The biggest way in which I was wrong in the book was I thought so the development of AI has gone faster than I was expecting, and the governance has gone slower than I expected. I never thought that governments would let companies get this close to something they could lose control over, without doing anything in the U.S. But I really hope that will change, actually.
Let me ask one thing. So physics would contribute to that, to this
yeah, absolutely.
interpretability?
Absolutely. First of all, one thing we see a lot when we do mechanistic interpretability is just like the brain develops modules that do different things. You have vision back here and hearing here, etc. We see a lot of that stuff happening in neural networks too, and you can actually train the neural network for the nerds in the room where the loss function encourages modularity. And then you can say, well, I don't understand how the thing works, but it consists of 17 different parts, and I can divide them apart and put certain constraints on who does what and who knows what. And this is how we do security in human organizations, for example. If someone is, you don't have to tell everybody in your corporation every single secret and give everybody weapons and so on. So that can help. And as I said, again, using machines to prove things about other machines. We physicists are good at figuring out how complicated systems work, right? So if that can be automated, AI is a complicated system. We can use machines to prove things about other systems and to get the guarantees we need. I'm optimistic that if you have safety standards, so the incentives are there, then just like biotech companies put many of their smartest people on making sure that the stuff is safe, the tech companies will also.
Okay. So.
Yes.
Oh, yes, please.
Hello, my name is Arnoud. I'm doing research and education at ETH AI Center and also with ALICE, the European network. My question is about the understanding of the world of AI models. So we saw, using physics for AI with Lenka and also using AI for formal verification or even grading maybe. The question is, what do you see is next? Like now there's already reasoning models, which is very much about mathematical or logical reasoning, how to maybe get a better model of the world, maybe using simulators, or what do you think is the next step in this direction to give these models a better physical understanding? Because they often fail, for example, visual language models and others at representing reality, and they miss completely. What is, in your opinion, maybe wish list style? Maybe is it a simulator? Is there maybe other more efficient things to go about this?
Anyone?
May I?
Yeah, yes, please.
So,
okay.
So I agree with Max's opinion on that. We will have automated mathematics, and so far, of course, all of the science is based on mathematics as a description. And if that part is automated, then I think there is a great change in the whole science. So in my community in Japan, so normally what we do is to make our computation faster by using AI. And it's not about generative AI. It's about machine learning. It's an old word, right? And now, because of this automated mathematics, which will be developed in a few years from now, I think a great part of science will be affected by this. And that is really a collaboration with AI for every scientist in the world, I think.
If I may follow, one thing that I would like it to see is somehow, 20 years ago when I was imagining what AI will do for us, I was imagining the boring stuff like cleaning my apartment, not like writing the poem about the place that I love, right? And that to me is a big surprise. That is like so good at the creative stuff, like it's amazing.
And it still can't clean your apartment.
And it's still clean my apartment. Yeah, exactly. So I would like really want to go to that, right? Yeah. That it actually does the things that we do not want to do in our place, like cleaning my apartment.
Okay. Okay, great. Oh, okay, please. Oh, yeah, please. Yes.
Thank you. Salama Belgali from the AI Career Accelerator. I'm coming back to, Max, what you said I'm a little bit kind of confused and a little bit also worried. I was a month ago at NeurIPS in Vancouver, and I heard your colleague, Dr. Rosalind Packard, talking about exactly what you mentioned. We don't want this super intelligence to kind of like control us. And it was kind of worrying, her talk about it. So my question is, are we just here like making assumptions or putting it like more in a moralistic way? Oh, we really need to be careful, to check if, the nuclear reactor is not going to explode before to build the nuclear reactor. Are we too late for that? When I see also the news from the couple of days ago, seems like there is a race, and this is becoming political. It's like people like the governments or like the nations who are who have that technology are going to be far away ahead, and there is so much laughing about Europe lagging totally and regulating something that they haven't even created. So my question is like do we really need to be worried here, or like what's going on?
Of course we need to be worried. I mean, the last year, in May of 2023, all the CEOs of the leading tech companies and so many of the top scientists signed this letter saying this could cause human extinction. And they were not joking. This is the first time since Oppenheimer that you had leaders in a field warning that this thing could destroy us. But at the same time, it's absolutely not too late. It's all about power and control, and right now it's we humans who control the machines, not the other way around. We just have to make sure to keep it that way. The race you mentioned is exactly the key part of the problem. We want to have a race to the top, like we have in biotech, where the companies race each other to who can make the medicine pass clinical trials first, not a race to the bottom the way it used to be in biotech when we got thalidomide that caused hundreds of thousands of women to give birth to children without arms and legs, And as soon as people in powerful positions in government realize that we're actually closer to building AGI that we could lose control over than we are to controlling it, they will realize that they will also lose control, and they will push very hard to put in some safety standards so that the companies then race to the top. And whatever you think about the new election in the US and so on, Donald Trump actually gave a speech very recently where he warned about losing control over machines. Elon Musk is very freaked out about losing control over machines. David Sachs, the AI czar, had a tweet recently where he says, I want great AI tools, I do not want a replacement species. So I'm hopeful that if all of you here also go around and tell people we don't want super intelligence, we want super smart tools, that we can get that.
But we also need to be very careful about one thing, because the way you are asking the question and the way you are answering, you're both assuming that the danger will be visible to us. But the danger is already there. Look at all the kids that are hooked on YouTube, suggesting them one silly video after another, instead of exploring the world and doing, and okay, maybe it is not bad. To me, it looks pretty bad. But we don't have understanding what actually is the consequence of these algorithms being in everybody's pocket has on the development and on the future of the evolution of our species. It is clearly changing what is happening, and to me at least it's already there, and nothing is really telling us that the danger will be some robot that will come and like in the movies. The danger is sneaking. It's kind of already happening without us really realizing. It's like the frog in the boiling water, right? I mean, when it realizes, it's like way too late.
Okay. So, one last question.
Kohei Ito from Keio University. I have a question to Professor Koji Hashimoto. You mentioned physics of AI. What are the chapters of your first textbook on physics of AI going to be?
That's a nice question. I'd like to write that textbook. And the first would be how to actually, so we need to give notions. And in physics, we have physical quantities or physical observables which actually can control everything behind the phenomena. So for example, the word entropy, that was invented in thermodynamics, But before that, there was no word entropy. And now we use the word entropy to actually quantify every phenomenon, right? So that kind of quantity is still missing in this AI understanding. So we need to find, develop more and more theories, and we propose more quantities which can hypothetically control or capture or characterize the AI behavior. And that would be the first chapter of it.
I see.
And then theory comes.
Right. So this, I mean, I guess this basics will be a kind of source of we hope, the source of controllability, or as well as this interpretability. So, yeah, thank you so much for this very inspiring talk, and also thanks a lot for joining us, all of everybody in the audience. Thank you so much.